In this video 5, I will show some additional properties of Boolean functions. First, let me correct minor typos that I had above. This thing is, of course, to equal 0. Yes, the way it's written, it doesn't even make sense. And another typo I had is in the general reproductive solution here. We didn't really evaluate fx, but x plus fx, which is actually f of g of x. I will make a PDF out of this document, and it will be available to the viewers of this video. I also said that I decided to skip the proof of this statement, but let me show at least the novel part of the proof, some important lemma, and the result follows from after using the lemma that I'm about to show. The result will follow from Hall's marriage theorem. It has two formulations. One is graph-theoretic and the other is set-theoretic. We rely on the set-theoretic form. And it is about system of distinct representative. So I assume that you are familiar with Hall marriage theorem, and if not, please go read on it. It's a very simple and very nice theorem, at least very nice to state, very easy to state. Another introduction I need to give to the lemma. Above we spoke about minterm normal form, which is this. This is minterm normal form of Boolean functions. But let me copy this because we will need it later. But there is also minterm normal form of formulas. So far, an atomic formula in the language of Boolean algebra was of the form some Boolean function equals 0. In minterm normal form of formulas, each atomic formula is of the form some coefficient times some minterm equals 0. To see how to go back and forth, so if we have atomic formula of this form, fx equals 0, so we can write f as minterm in minterm normal form. And if this thing equals 0, this is the same as each minterm equals 0. So here I write a logical conjunction. So we get conjunction of atomic formulas in this form. And therefore, it is enough to consider a system of equations where each equation has this form or the negation of this form by converting the formula to minterm normal form. Now, what I'd like to prove is the following lemma. The system AI x to the AI greater or equal BI, and as usual, this is a finite system. These i's are taken from some finite index set, and each AI is a bit string, and this AI and this BI are constants, Boolean algebra elements. So has a solution. So it's a multivariate system. Yes, it's capital X. If and only if BI, BJ are disjoint whenever AI not equal AJ. So first, let me show you that necessity is immediate. As we said before, all minterms are disjoint. So those are disjoint sets. Which reminds me, so forgive me for the interruption, I have to justify set-theoretic language. I always speak in set-theoretic language. I have to justify this. There is the famous Stone's representation theorem for Boolean algebras. It says that any Boolean algebra, each element can be seen, can be not only seen, but can be identified can be identified. Let's write identified with a set quite constructively, while the Boolean operations are the standard set operations. So this gives us full justification to always look at Boolean algebra elements as set, as indeed they are sets. Stone representation theorem has much more far-reaching consequences, mainly about a topological duality, which comes with a whole very interesting topological results and considerations and duality between Boolean algebras and certain topological spaces. But we will not get into it. So back to our setting. So minterms are disjoint sets. If I conjunct them, intersect them with another set, they will still be disjoint. So we are going to say that Bi is a subset of some set. And if those sets are disjoint, then of course their subsets are disjoint. Therefore, it is very easy to see that this condition is necessary. So necessity is immediate. Now, to show sufficiency, we go by induction, number of variables in X. Okay, so first, we assume that all AI are different. And now I see that I made a mistake. I don't need this AI here. Let's take the more simple case where there is no AI here, and we don't really need it. We will see later on that we don't really need it. So we assume that all AIs are different because if not, then if X to the AI, let's say A1, greater or equal B1, and X to the same A1 greater or equal B2, then I can simply write it as X to the A1 greater than B1 union B2. So without loss of generality, we assume that all AIs are different. And now for a single variable, we proceed by induction. So that's the base case of the induction. The general case is X greater than B1 and X prime greater than B2. And we can see that the solution is immediate. You can, if B1 and B2 are disjoint, then you can simply choose X equals B1. If you choose X equal B1, then of course B1 is greater or equal to B1, and B1 prime greater or equal B2, this is the same as writing by the definition of the order. It is equivalent to write that, but we did say that B1 and B2 are disjoint, so we proved for the case n equal 1. Now for the induction step, separate distinguished variable X. So suppose X is now not part of capital X, as we shall see, and write the system as, so we have a system of the form I in I, X times X to the AI greater or equal BI, it's not the same B. And here we will have X prime. Here, let's call it C. And yes, let's change the indices. Now, by induction hypothesis, suppose we have a solution, we have an X satisfying this system. And suppose now that the set of indices I is non-empty. Of course, if both I and J are empty, then we have no system. If only I is empty, then we can solve for X prime instead of solving for X. So let's just assume that I is non-empty. Now we can come up with an ansatz. Just set X equals the union of all bi. Now let's see if it works. We have these two systems. And now x equals this thing. Let's put it here. And in this thing, I can put x ai right here inside. But we already know that ai, well, I need to change the indices, so let's call it m. Now this greater or equal than if I take bi here, because there is a union here, and I take only one element from the union, therefore I'm greater. So this is greater or equal than if I take only I, but by our assumption here, by the induction assumption, and the induction hypothesis, this is greater or equal bi. And similarly, so here will come the negation of this. Let's put it right here inside. So the negation of this is going to become the intersection, and here this is going to be negated. And now we assume that the bi's and ci's are disjoint. So I want to write here cj, and I need to show that cj is less or equal this intersection. This is the big thing. Yes, it's in the left side of this greater or equal. I claim that when I put cj here, there is really greater or equal because this cj is smaller. And indeed, this inequality, let's move it to the right-hand side. By definition of the Boolean order, this is equivalent to say that this thing is 0, which is the same as putting the cj here, but this just follows from the assumption that the bi and cj are all disjoint. So I can put the cj here. And this is, of course, greater or equal cj, again, by the induction hypothesis. So we prove the lemma, which is true in any Boolean algebra. Now, when you have a system of equations, a system of inequations, of the form ai x to the ai not equal 0, remember that what I wanted to show is this, that a set of Boolean functions over atomless Boolean algebra have a common non-zero if and only if none of the Boolean functions is identically 0. So what I really want is to write this as greater than some bi, and this bi should not be empty. And if I find such a bi that I can choose from here, then the above lemma, then what we proved right here, guarantees that there is a solution. And this comes down to system of distinct representative, just the whole marriage theorem. If I can choose for each I a subset of this set, such that this subset is disjoint for different i's, then because of the lemma, I have a solution for this, and this is not always guaranteed. So it's going to depend on the cardinalities of AI by whole marriage theorem. Whole marriage theorem says that there is a system of distinct representative if certain cardinality conditions hold. But in atomless Boolean algebra, all cardinalities are infinite. And when cardinalities are infinite, whole marriage theorem tells you that there is always a solution. And therefore, this thing always has a solution as long as AI is not 0. This system always has a solution. There is X satisfies all systems simultaneously, if and only if this AI is not 0. So that's for this matter. Some more additional topics just to get a little more practice with Boolean functions. Let me show you some nice properties of Boolean functions. For any Boolean functions f, univariate in this case, we have, let's take the conjunction over all x in the Boolean algebra of fx. I evaluate the function on the whole Boolean algebra and I take the intersection. So what does it equal? Well, surprisingly or not, it equals f0, f1. Moreover, the union is going to be f0 union and f1. And the sum, which is also called the Boolean derivative, this expression is called the Boolean derivative, will also satisfy this. Now I will demonstrate the proof only for the intersection, and the rest is exactly the same. So we know that I can intersect with the same element twice, yes? So AB is the same as AB. There is no problem intersecting with the same element twice. And so I can write it as fx times fx prime. Now for any Boolean function, fx times fx prime, let's write it. So if f is ax plus bx prime, and fx prime is going to be this. Now, if you are familiar with the binary decision diagrams, then you know how to easily multiply or do any Boolean operation over things in that Boolean functions that are written like this in Boole's normal form. Just multiply the coefficient very trivially. So here the coefficient of x prime is b, here it's a, so here just comes ab. And similarly here will just come ab. Now abx plus abx prime, it simply equals ab. And what is ab? Well, ab is nothing but f0, f1. So we get, in particular, we get this identity. Okay, let's prove another nice property. Trilinearity. F of x plus y plus z equals fx plus fy plus fz. I never encountered an object in mathematics that satisfies this property. And this is very easy to show in algebraic normal form. Suppose fx equals ax plus b. Then fx plus y plus z equals ax plus ay plus az, which if you evaluate this thing, you will see that b is added with itself twice. When it is added with itself twice, it becomes 0. When it is added for the third time, it reappears again. Yeah, so it's very easy to see that this equals this. Another interesting property, which is a special case of something that we will need later, fx equals fx. And this we can also do in algebraic normal form. So this is fx. Let's write ffx. It's this. And now let's write ffx. It's this. Now let's start distributing. A comes inside. A comes inside again. AB plus AB, that's 0. And here we got f again. So maybe indeed, I said it's a general case that we will need later, so let me dive into it right now. Let me throw some ugly term, the term weakly omega categorical theory. Now, you probably know that an omega categorical theory is a theory in which all its countable models are isomorphic. Now, there is a theorem by Rilnardzewski that says Omega categorical theory is an equivalent definition of omega categorical theory is the following. There are only finitely many formulas with fixed number, or let's say fixed, finitely many fixed free variable symbols up to logical equivalence. Now, weakly omega categorical theory, I define by, let's copy this statement. Weakly omega categorical theory would be, in weakly omega categorical theory, there are only finitely many formulas with finitely many fixed free variable symbols and constant symbols. So if I tell you, write to me a formula, but those are the only free variable symbols and constant symbols that you can use, and you can only give me finitely many such formulas up to logical equivalence, then we call it a weakly omega categorical theory. Now, the theory of atomless Boolean algebra is weakly omega categorical. Why is that? First, it is enough to consider quantifier-free formula, since we have a quantifier elimination. Now, consider minterm normal form, or let's say formulas in minterm normal form. So they are Boolean combination. They are simple Boolean functions. Of atomic formulas. In n variables, there are 2 to the n simple Boolean functions. How many atomic formulas we can form with n variables and k constants? Well, they are all of the form c times some constant times some minterm. So the number of possibilities, the number is k times 2 to the n. There are 2 to the n minterms, if that's the number of variables, and k constants. So in our case, n equals k 2 to the n. So the final number is 2 to the 2 to the k 2 to the n. It's triple exponential. That's an upper bound of how many formulas up to logical equivalence you can write with prescribed finite sets of constants and free variables. Now, why is it interesting? Because in weakly omega categorical theories, we can have recurrence relations. So suppose you have a formula defined by recurrence relation. Let's say it has a free variable, and let's say it exists y, such that here I use the recurrence relation, I use the n-1, and let's say I conjuncted with another given formula. And of course, I need the base case of the recurrence relation. It all goes bottom up. So this equals whatever. And now I try to unfold this recurrence relation. Since there are only finitely many formulas, when I unfold this recurrence relation, at one point, I will get a formula that I got before. While unfolding, due to the finiteness property, there will be a loop, either a fixed point or a partial fixed point. In a fixed point, we get the same result for n and n plus 1. In partial fixed point, the distance between the equal formulas, the equivalent formulas, is not 1. And if we really in practice want to enhance languages like the language of Atomless Boolean algebra with recurrence relations, if the recurrence relation is monotonic, then of course we are guaranteed to obtain a fixed point. But if it is not monotonic, then we can define a fallback. We can say that if there is a partial fixed point, then either return the part that is looping or return some default formula. All other such trivial remedies are expressible in the language. This is a more general case of this. There are also only finitely many Boolean functions with prescribed variables and constants. So this holds not only for formulas or also for functions. So at the same way, I could also define a Boolean function recursively. Okay, I see that here I forgot to put some parameter. Let's put it now. Let's say something like this, or maybe to make it more interesting. So it will be a bivariate Boolean function. Let's say like this. So yeah, the same fashion, the same way, I can define a recurrence relation of Boolean functions, and I can unfold such a theory with recurrence relations of formulas and Boolean functions into the theory without, precisely because of this weakly omega categoricity. Now, this is, of course, quite expensive in the worst case, because yeah, that's the upper bound we know for how many formulas you can reach. But I can say that in the case of interest, which we will show in the guarded successor, which somehow it looks exactly like this, in some simple case, you reach a fixed point surprisingly fast. I don't know for now what exactly going on there. I could prove it for a special case, but I can say that empirically, the formulas of interest converge much faster. So maybe this bound is not a good upper bound. I don't know.